Hello coding champions, welcome back to Strictly Coding. If you declare an array in C++ of 10 integers, for example int arr of size 10, then consecutive 40 bytes will be allocated if an integer occupies 4 bytes, and the array name arr will represent the base address. We can also declare a pointer to integer, let's say int star ptr, and we can say ptr equal to new int of size 10. So then we can dynamically allocate 40 byte again consecutive, and ptr can store the starting address. And thereafter we can use ptr the same way we can use an array arr, okay, to access the memory. Therefore, can we say that an array in C++ is a glorified pointer? In today's video, we are going to dig deep, coming right up. Hey, this is Subrata Kumar Dey. I am a university teacher teaching computer science courses over 1.5 decades. If you are a coding enthusiast and new to this channel, consider subscribing and share with your friend. Also, press the notification bell so that you don't miss any future update. Okay, to understand whether an array is a glorified pointer or not, first we have to understand the pointer arithmetic. So I'll be talking about the pointer arithmetic a little bit, and then we'll see how it helps us, the programmer, actually to manipulate the array the conventional way with the help of the pointer arithmetic. So we'll prove that in C++ array actually follows pointer arithmetic, in many programming languages too. And we'll be sending a collection of elements to a function as an array as parameter to that function, also as a pointer as parameter to the function, and we'll see is there any difference. Okay, so therefore at the end of the discussion we will be in a position to make our conclusion whether an array in C++ is really a glorified pointer or not. So stay tuned till the end of the video. Okay, so if you look at the screen, I have declared a one-dimensional array 1D of size 5. Okay, and if an integer occupies 4 bytes, so 20 bytes are allocated. Okay, so let's say the starting byte number is 708. And so it will end at 727. Okay, so these 20 bytes are allocated. Now the array name alone, now if we say cout 1D in C++, we'll get the base address 708, which is also the address of the first element. So if we try to say what is the address of the first element, it is nothing but the base address. Okay, now if you add a number to a normal integer, let's say if you have an integer x whose value is 10, and if you say x plus 1, you will get 11. But if you add a number, if you add 1 with a pointer with an address, not necessarily you will get the next byte number. Okay, so suppose the 1D represents 708. Now if I say 1D plus 1, not necessarily it is 709. It will be actually 712. Okay, so plus 1 with a pointer or an array name, that means plus 1 with an address will give us the address of the next element, not necessarily next byte. It will be next byte if the element is character, okay, because character occupies 1 byte. So therefore if we say 1D, we'll get the address 708. If we say 1D plus 0, the displacement is 0, we'll still get 708. If we say 1D plus 1, we'll get the address 712. If we say 1D plus 2, we'll get the address 716. And the way we can dereference a pointer, we can also dereference any address. So 1D plus 2 represents 716. So if we dereference that, we'll get the value 33. Okay. So I have written a C++ program already for you. Now if you see here, we have declared an one-dimensional array 1D with 5 elements. Now we are printing the elements using the conventional notation, that is 1D sub I. Okay, and now we are actually trying to print the addresses. So if we say cout 1D, it gives us the base address, okay, of the array. Now, normally the addresses are printed in hexadecimal format. So to see the decimal equivalent, I have converted them to long. I could do it long, but I made it long in case I have very high amount of RAM and the byte number is at the upper end of the RAM. So long is safer. Okay. So 1D plus 0 will give us the element of, address of the first element itself, which is the base address. So the base address and 1D plus 0 will print the same thing. 1D plus 1 will print the address of the next element. 1D plus 2 will print the address of the third element. So according to the diagram, 1D should print 708, 1D plus 0 should print 712, 1D plus 2 should print 716. Okay, so 1D plus 0, 1D plus 1, 1D plus 2. Now this 1D plus 2 is an address. So if we dereference like a regular pointer, we'll get the value 33. So if you look here, we are actually dereferencing 1D plus 2. So this should print actually 33. Now if we use the normal conventional way, see out 1D sub 2 using the index 2, then also we'll get 33. So therefore we can say this is actually the convenience for the programmer, this notation, but actually it is interpreted like this. So when we use an index, basically pointer arithmetic is applied, as we can see here. So if I run this program, as you can see, if I just compare it with the diagram here, now you can see the elements are 11, 22, 33, 44, 45. Fine. Base address of the 1D array, that is which is 1D. Okay, so spelling mistake, sorry, which is 708. So 1D plus 0 also 708, that is 63,56,708. Now 1D plus 1 is 712. Okay, 1D plus 2 716. You see, now it is giving the address of the next element. Okay, so if you plus 2, address of the element which is after 2 elements. Okay, so that is the way. And if we dereference, we get 33. If we use the conventional way, we also get 33. So basically conventional way of manipulating array actually internally use the pointer arithmetic. Okay, so that is for one-dimensional array. Okay, now let's talk about the multi-dimensional array. Now let's say we have a two-dimensional array 2D having 4 rows and 5 columns. So if I ask you how many elements are there in the two-dimensional array 2D, anybody can say that there are 20 elements. But beware, I'm not asking how many integers. Okay, so if I ask you how many integers, then the 20 is the right answer. But if I ask you how many elements, then we need to think about it. Okay, now if you look back to the one-dimensional array, how many elements are there in 1D? We can safely say there are 5 elements, because elements are integers. So number of elements and number of data are same, because that is the lowest dimension. So therefore the elements are the data that we store, okay, which are the integers. Now in case of two-dimensional array, the number of elements are actually number of one-dimensional array. Okay, so the rule of thumb we can apply, because pointer arithmetic actually follows this rule. Okay, so if you think of a one-dimensional array, the number of elements are actually number of data, because that is the lowest dimension. So you cannot have any sub-dimension. Therefore the elements are data. So number of data is the number of elements. Now the number of elements of a two-dimensional array is nothing but the number of one-dimensional arrays. Okay, similarly number of elements of a three-dimensional array is nothing but number of two-dimensional arrays within that three-dimensional array. Okay, so therefore in this particular diagram, if we ask how many integers are there, how many data, how many integers, then we can say there are 20 integers. Okay, because 4 rows and 5 columns. But if I ask how many elements are there in this two-dimensional array, then we know that one-dimensional arrays are the elements for two-dimensional arrays. So therefore we will have 4 one-dimensional arrays. So the answer will be 4. Okay, why we need to view the logical organization like that? Because if we print 2D, simply the array name, it will give us the base address. Okay, now let me show you the data, some hypothetical data that I get from executing this program. Now let's say the base address of the 2D array is 628. Okay, now for one dimensional array, if I say 1D plus 1, I get the address of the next integer. But for 2D array, if I say 2D plus 1, I get the address of the next row, because next row is the next element. Next 1D array is the next element. So this 1D array is the first element. Okay, then this 1D array is the second element of the 2D. This 1D array is the third element of the 2D, and this 1D array is the fourth element of the 2D. So if I apply pointer arithmetic with the base address of a 2D, I get the address of the next element. Now here the elements are rows, 1Ds. Therefore, 2D, if the address of 2D base address is 628, 2D plus 0 also will be 628. Now 2D plus 1 will give me the base address of the first row, I mean the second row, which is 648. Okay, because this will occupy 20 bytes, 5 integers, so 628, so it will be 648. Okay, so 2D plus 2 will give us 668, and 2D plus 3 will give us 688. Okay, so that is the meaning. So therefore, if we want to apply pointer arithmetic plus 1 plus 2 plus 0 with 2D, we get the address of the elements, which means that we get the address of the 1D. Okay, now we have to use another subscript to access the elements within that 1D. Okay, so that is why we need to use different indices for different dimensions. Okay, now let me explain that with the help of the source code. Okay, so now we have the 2D array. Okay, 4 rows, 5 columns. We put some random values, less than 500, fine. Now you see, we are trying to print the base address of the 2D, which is according to our diagram, which is 628. Okay, which is 628. Okay, now if I say address of the 0th element, which is the first row actually, which is the one dimensional array at position 0, which is nothing but the first row, which also will be the same, which also will be the 628. Okay, because this is also 628. Okay, now if we say the address of the element of the index 1, that means 2D plus 1. Okay, so 2D plus 1 will give me the address of the next element. So in this case, next element is the next 1D. That means it will give us 648. Okay, not the address of this value. Okay, address of the second 1D. Now if we say 2D plus 2, again we'll get address of the 1D array at position 2. That means 668. Okay, so now 2D plus 2 gives us 668. Okay, now listen carefully. Now this 668 is the address, but how compiler interpret that address, that is important. Now compiler is interpreting that address as the third element of the 2D. Now we need to shift the dimension. Now we are in the now we are within the second dimension. Okay, so therefore if we say 2D plus 0, 2D plus 1, 2D plus 2, we get the address of the elements of 2 dimensions, okay, which are the address of the 1D array. Now we get the address of the third element, which is 668. Now still we are in the the higher dimension. Now we have to shift the dimension and get inside the lower dimension. So if we dereference the address, we get the value. Okay. Now let me compare it with the 1D. Okay. Now if I dereference 716, we get the value which is an integer. Now, but in this case, if we dereference this address 668, we get the value which is not an integer, which is a one-dimensional array. Okay. So after dereferencing also we'll get the one-dimensional array. That means we'll get the base address of the one-dimensional array. So after dereferencing 668, we'll still get 668. But before dereferencing, 668 was representing the third element of the 2D. After dereferencing, 668 becomes the base address of the 1D. Okay, so that is the important thing to understand. Okay, so we shift the dimension. Okay, so therefore if I say 2D plus 2, it gives the address of the third element of 2D, which is 668. Now if we dereference, we will still get 668, but now it is the base address of the 1D. So we actually move from two-dimension spectrum to, we narrowed down and we shift our focus into the one-dimension spectrum. Okay. Okay. Now if we apply arithmetic with this, we will be actually getting the address within the 1D. Okay, that means we'll be getting the address of the columns. Okay, that is the thing. Okay, so now therefore this gives us the 668. Okay, so this is basically the address of base address of the 1D now. Now if we apply plus 3, then we shift elements within 1D. So plus 3 will give us the plus 3, so plus 0, plus 1, plus 2, plus 3 will give us the address of 327, which is 680. So 668, so you just add 4 bytes, okay, we get 680. Okay, so that is the meaning. So therefore please don't get confused with this and this. Both will give you the same address, but the addresses are viewed differently. Okay, so here the address is viewed as the address of the third element. Here the address is viewed as the base address of the 1D. Therefore with this, if we apply arithmetic, with this if we apply arithmetic, we get the address within 1D. Okay, so plus 3 will give us the address of the elements of the index 3 within 1D, which is the address of this 327, which should be 680. Now if we dereference this address, then we get the value 327. So if we dereference the whole thing, okay, so we are dereferencing the whole thing, we'll get the value 327. Okay, so that is how actually pointer arithmetic is applied for any dimensional array. All we need to understand that the elements of 3Ds are 2Ds, elements of 4Ds are 3Ds. So if we apply arithmetic with the topmost direction, we are actually getting address of the elements at the topmost direction. Okay, so that is the thing. Now we could also do that using the conventional way, like using index. Okay, so 2D plus 2D of 0, it's a two dimension. So 2D of 0 will give us the first element, which is a 1D. That means it will give us the base address of the 1D. Okay, this will also give us the base address of the first element 0 0. This will give us the address of the second row in position 1. Okay, this will give us the address of the third row. Okay, and this will give us the address of the fourth column of third row, and this will give us the value of the fourth column of third row. So this is the conventional way that we can use, we can apply with an array, but ultimately it applies pointer arithmetic, that is demonstrated here. So if I show you the output now of the rest of the programs after 1D, so this is the 2D elements. Okay, so now if I show you the diagram here, these are the 2D elements. Okay, so you see 41, 467, so these are the elements. Okay, now base address is 63 lakhs 56,628. So I have written it here, 628. Now 2D plus 0 also, of course, it will be 628 because address of the first element is also the base address. Okay. Now 2D plus 1 will give us 648. You see 648. Okay. So 2D plus 2 will give us 666, which is 668. Okay, 668. Okay. Now if we dereference 2D plus 2, we will still get 668, that you can see here. Before dereferencing 2D plus 2, we got 668. After dereferencing also, we got 668. But this is the address of the third element of the 2D. This is the address of the base address of the 1D array. Okay, that's the difference. So therefore, with this, if we apply arithmetic, we get the address, we shift the address of the elements of the 1D array, which are the columns. So now if we plus 3, we get the address of the fourth column within that 1D array, which is the address of the 327, which should be 680. So we got 680. Now if we dereference that address, we get 327. Okay. So this is equivalent of using the conventional way. Okay. So you can check it out. So therefore, now after understanding that actually pointer arithmetic is applied in array manipulation, so we can say that array is a glorified pointer. But hold on, there is a thin line of difference that we need to understand. When we declare an array, now if you look at the code, now let me show you the another code. Okay, so let me comment this. Okay, so now if we declare a pointer like ptr in star ptr and we allocate memory for 5 integers, okay. Now 1D also is an array of 5 integers, capacity 5. Now we use a pointer and we allocate dynamic memory to store 5 integers. And we can also use ptr as an array, okay. So we could use ptri, no problem in that, okay. So therefore we can actually use pointer interchangeably as an array once the pointer is given some allocated memory, okay. Now if I try to show you, I'm storing some random value up to 10 to ptr after allocating, okay. Okay, now let me comment this and let me show the elements of the ptr, okay. So let's say this is 5. Okay, so we are going to print the ptr. Okay, so fine, so we have a one-dimensional array, okay. Now we allocated some elements to the one-dimensional array and we are trying to print the values of that one-dimensional array, no problem. Let's say 5. And if we run that, we'll see both 1di and ptri is fine. So we can actually, because 1d gives us the base address and within the index, within the subscript, if we use index, it applies pointer arithmetic. ptr is a pointer, so it applies pointer arithmetic. So they're basically same, okay. So if I try to run this, sorry, something went wrong. 5, so I assign some random values. Okay. Oh, I should not call that. Okay. Okay. So now you can see that some random values is assigned to PTR up to 10, so 17409, so PTR I, okay, and this is ARR I, okay. So no problem whatsoever, okay, okay. But now, so therefore we can convince ourselves that a pointer and array name can be used interchangeably uh, to represent a collection of data, of homogeneous data, okay. Now if I try to pass that array as a parameter to a function, then what will happen? Okay, so now I'm going to calculate the number of elements of that array. Now you see 1D is an array, okay, and now size of is an operator. So if I say size of 1D, it will give me the number of bytes given to 1D. So since there are 5 integers, the size of 1D will give us 20, okay, in terms of bytes. So it will actually size of the array, that means the number of integers will be the total number of bytes divided by number of bytes per element, which is integer. So this will give us 20 divided by 4, which is 5. So now it will tell that number of elements in 1D is 5, okay, okay. And the 1D elements are, now we run the loop 0 to size of 1D, which we have calculated, okay, and we can print that array elements, okay, fine. Now let's see what is interesting about PTR. Now we try to see the size of the PTR, okay. Now even though we allocate memory for 5 integers, so the allocated dynamic memory size is 20 bytes, and PTR will be storing the starting byte, but the size of PTR, will it give us 20 or not? If it gives us 20, then no problem, we can say that size of PTR will be 5. But if it doesn't gives 20, then it will be a problem. So let's try to run that first, and then we'll see what it gives, okay. So we tried to print using size of PTR. So if size of PTR is 5, then we should be able to print the values correctly, okay, okay. Now I am using 5 to assign the random value, so we will not have any impact here. But when we try to print, will it print 5 elements or not? That depends whether the size of PTR is 5 or not. Now of course for size of 1D it will be 5, because size of 1D will give us 20 bytes divided by size of integer, so we'll get 5 here, okay. So it will run, this loop will run 5 times, but will this loop run 5 times or not? Okay, so let's see. So if you see, the size of 1D is the array name, okay, is 20 bytes. So therefore the number of elements in 1D is 20 divided by size of int, which is 5, because size of int is 4. And so the loop run 5 times and we print the values. But on the other hand, the size of PTR is 4 bytes. It's not 20 bytes. Because array name represent the base address, but the pointer actually represent the address stored inside the pointer. So size of pointer is a variable, independent variable, PTR, okay, which takes 4 bytes to store the byte number, because it's a 32-bit addressing machine, okay. If it is 64-bit addressing, then it might be 8 bytes too. So basically it tells how many bytes needed to store an address, because it is a pointer and its job is to store an address. That is why it is not telling how many bytes are dynamically allocated for 5 integers. So it is not telling 20 bytes. It is telling the byte number requirement for an address, and that's the difference. Okay. So if you want to send an array as a parameter to a function, then from the array name you can actually get the number of bytes, so you don't need to tell the size of the array separately. You can calculate the size. Okay, that is the number of elements. Okay, so size of the array name divided by size of the element, so you can get the number of elements of that array, so you can run the loop without having the size. But for PTA pointer you cannot actually do that. Okay, because from pointer you cannot calculate how many elements are dynamically allocated. Okay, you cannot do that. You just get the base address. So that's the difference between array name, using an array name, and using a pointer. Okay, and therefore since it is 4 bytes, so now divided by 4 is giving 1, so it is actually printing the first element. Okay, but if I change it to 5, then we'll run the loop 5 times, then we'll get all the values. Okay, okay, so now we get all the values, but still the size of PTR divided by size of int give us 1, because size of PTR is 4 bytes. So we cannot actually use that size of to determine the number of elements. Okay, in case you use a pointer instead of an array to run the loop. Okay, so that's a difference that we have to keep in our mind. Okay, the next thing is, okay, fine, so now we have a array ARR, sorry, 1D. We also have a pointer PTR. Now if I want to print the average of these arrays by calling a function, let's say 1D. Okay, so we are calling print average function, just passing the 1D. Now 1D is the array name. So do we need to send the size of the array here, from here, like comma 5? Is it needed or it's not needed? Now we have seen right now that we can actually calculate how many elements are there from the array name. Okay, so from the array name we can actually calculate how many elements are there. Now we might think it is not needed. Okay, so let's try to calculate in the function print average. So that is the print average with one parameter, which is the array. Now we are trying to calculate the size of ARR. Okay, and we are running the loop for size times. Okay, from 0 to size minus 1, and we are accumulating the sum. Okay, and we are dividing it by the number of elements, so we should get the average. Okay, to be printed. But the problem is, will it work? So let's see. Now we call the one parameterized version, that is actually called function overloading. So we can have multiple definition, one with one parameter, one with 2 parameters. Okay, so that is called function overloading or method overloading in case of class method. If you're not familiar with that, there is a video, and check for the card there for understanding function overloading. Okay, so this will be executed, but the problem is, if I run this, first of all it will give me a warning. Okay, why that warning is, let's run and understand that. Okay, now we have called the average function. Okay, so printing array elements from print average. Now instead of printing all 5, it is printing only 1. So the problem is, inside the function it failed to use that size of ARR, okay, which was supposed to give 20, and divided by the size of integer, which was supposed to give 5. So it could run the element array loop 5 times and it could print all the elements, but it did not. So it did exactly the same what it did with pointer, okay, within main. So why it is like that? Because here, if you look at the main, here the size of is working fine because 1D is your original array name. Okay, but when you pass it to the function print average, Now in print average, you might think that it's an parameter, it's a reference of an integer array, but basically it's a pointer. Okay, basically it's a integer pointer, but instead of int star arr, we use that subscript to understand that it's the address, base address of an array, not the address of a single integer. Okay, just to differentiate that, we use this notation. Okay, so if you want to send an array, you have to use that subscript instead of int star. But deep down, it gives you the size of the pointer, which is 4. Okay, because it is 32-bit addressing, and that is why in run it is printing only one value, and the average of one value is the value itself, which is 11. So instead of 33, it is printing 11. So the point is, if you want to send an array as a parameter to a function, from the parameter you cannot calculate the size. Okay, because that will give you the size of the pointer, not the allocated memory. Okay, you need the actual array name, not the parameter, because the parameter is basically is a pointer. Okay, which receives the base address of your array. Okay, so therefore what we need to do, we need to send the size also. Okay, so instead of calling the one parameter version, now we'll be calling the two parameter version. Now in this case we know that it is 5. So if we go back to the two parameter version, now we receive the size, so we don't need to calculate the size, which will be wrong. That is proven. So therefore we are giving the size, and we are running the loop for s times, which is the parameter size. Okay, and we total then, and we print the average divided by s. Okay, so if I now run this, now I'll get the correct average. Sorry, so recompile and run. Okay, now you see the printing array elements from print average. Now the loop is running 5 times. Okay, because we have given it as a parameter, so it is printing the average 33. Okay, cool. Now to prove that, to reinforce, okay, as the last nail on the coffin, that the array name is a pointer, we will actually pass the pointer ptr. Okay, so now instead of sending the array 1D, we will be sending the pointer ptr, which also store 5 elements after allocating memory. So that also will work. So now ptr will be received in arr. Now see, that means it's an array, it's a pointer, sorry. So basically it's a int star pointer, because ptr also will be received in arr. Okay, and accordingly it will show the elements, okay, which are the random values less than 10. So now if I call this, this will print the elements of ptr and the average. Okay, so let's see. Okay, so now you see the printing array elements from print array, so 17409, which was the elements of ptr, and the average of these elements are 4.2. So therefore if we want to conclude, we can say that an array is a glorified pointer. Okay, now you know the answer. Yes, they applied the pointer arithmetic internally. However, array name does not occupies any additional memory, but if we use pointer itself is a variable which takes some memory to store the address. Okay, that's the difference. And also we cannot send neither array nor pointer as a parameter to a function without sending the size, because it is not possible to calculate the size inside the function from the parameter. Okay, because the reference to an array is basically a pointer. Okay, so that cannot tell us the total number of bytes occupied by the array. So hope this clarifies the confusion about the array, and now we can safely say that yes, in some extent, in some way, we can say that C++ arrays are actually glorified pointer. Hope this helps. If you enjoyed the video, please give a thumbs up and share with your friends. Also press the notification bell so that you don't miss any future update. Thanks for watching. See you in the next video. Peace.